I'd like to show you how to use this virtual oscilloscope because it's going to show up later on in your lab. Now, an oscilloscope is basically a tool used to measure different kinds of waves. In this case, we're going to be measuring sound waves. So in this case, this is the oscilloscope. And you can see what's happening right now, and that it's basically the waveform, this part here in the green, is bouncing up and down because it's recording and analyzing the sounds of my voice. I know that because over here in the input it says live input, meaning that it's taking the input directly from my microphone. And if I keep on talking and I freeze it like that, then we basically get a snapshot of what the waveform looks like for that instant in time. If I unfreeze it, it goes back to normal. There are a couple things that are important about the waveform here and the settings on the oscillator, and there are a couple that aren't so important. So this one, the oscillator gain, by increasing the gain, it'll basically increase the size of the waveform. For what we're doing, that doesn't really matter. Seconds per division tells you the time that it takes for one box along the horizontal direction. So I'd like you to think of the horizontal direction, or the x-axis, if you will, as being time. So this basically just sets the value of one box. So one of these big boxes is right now 1 millisecond long, right? So this is 1 millisecond, 2 milliseconds, 3, and so on. Volts per division, again, so it's voltage along the y-axis or vertical axis. And again, that doesn't really matter for us. We're not looking for really deep information about the wave. So we just need it to be large enough that we can actually see what's going on. In this case, it's 5 volts per vertical box. And right now our live input is basically limited to 5 volts. So that's why sometimes you'll see the tops of the waves being cut off and turn into kind of squares. Like if I go, whoa, like that, then the tops of the waves are basically cut off and they just look square, which is not necessarily what we want, but doesn't really matter for us. And these two things, the horizontal offset and the vertical offset, just allow me to move the wave around when it's frozen on the screen. So I'll do those. I'll do those later on. I don't really play with the vertical offset too much, but I do sometimes adjust the horizontal offset. We'll see why. Okay, so let's just look at a wave that is a sine wave, like this. Okay, so this is a sine wave. It's no longer recording my voice, and it's just frozen in time. Okay, so this looks like one of our transverse waves, or for those of you who remember your math course, your sinusoidal function. So in this case, the amplitude is 5 volts, right, which is basically set over here. And it says here the input wave frequency is 250 hertz. So that means that somehow what's happening along the time axis, along the x-axis, is related to 250 hertz. And so how that works is, what we need to do is we need to basically count how many of these large boxes, well, I guess we can do the smaller division as well, but in this case, all we need to do is count how many of the large boxes make up one period, because again, we're talking time here, one period of the wave. So I'm going to start on the axis, right at 0, 0 basically, and I'm going to count. Let's see, I have 1, 2, 3, 4 large boxes that make up one period of the wave, one cycle of the wave. So that means because it's 1 millisecond, right? Milli means 1/1000, just like a milligram or a millimeter. So I have so in other words, my period is 4 milliseconds. 4 milliseconds from the start of the cycle to the end, 4 milliseconds. So how do we go from the period of 4 milliseconds to the frequency of 250 hertz? And the answer is you just need to remember that these two quantities are related by a reciprocal relationship. So in this case, if you take 250 and then you take its reciprocal, you would actually get 4 milliseconds. So 4 times 10 to the negative 3 seconds. Okay, so that's basically the relationship. If I increase the frequency. So maybe I'll make it like, I don't know, 500 hertz. Can I do that? Close enough. Oh, maybe I can type it. Yeah, there we go. I can type it. Hey. Okay, so 500 hertz. Now for 500 hertz, you can see that for one cycle, again, if I start at the origin, one cycle is 1, 2 of these large divisions, which corresponds to a total period of 2 milliseconds. And if I take the reciprocal of this, 1 divided by 500, 1 divided by 500 hertz is actually equal to 2 milliseconds. So there is actually that correspondence. It's a little unusual, but it's that reciprocal relationship. That if I take the reciprocal of this number, I get the period. I get the time it takes for one cycle of the wave. Okay. So what I'm going to do now is I'm going to just hum a note. So you can see that, I'm going to go back to live mode here for a second. There we go. So again, this will be all kind of wacky because it's just listening to my voice. And that's because my voice is made up of many different frequencies. The sound of my voice is made up of many different frequencies. But what I'm going to do is I'm going to hum a note, right, as best as I can. And I'm going to freeze that so that maybe we can see what the frequency or the period of that note is. So here I go. Okay. Kind of looks weird. And that's partly because I have a lower voice, I guess. I need to actually increase the amount of time per division. Right now, I'm kind of zoomed in too close, but if I increase to 2 milliseconds per division, now you can see that this is not a very nice looking sinusoidal wave, but nonetheless, there is a periodicity to it. Right? If I started here, I would go up and down and back to where I started again. So since we'd like to be able to, it's helpful if we can read large boxes. What I'm going to do is I'm going to adjust the horizontal offset so that it doesn't really matter. I just want to have, I like to have the axis of the wave at the start of one of these major divisions. So if I start it there, then I can count. I have 1, 2, 3, and not quite 4. Not quite 4. Not quite 4 major divisions. So I have 3 and 4 minor divisions, and each minor division is 0.2 of a major division. So in other words, I have 3.8 divisions, and my seconds per division is 2. So in this case, if I want to know what the period of this wave is, I'd take 3.8 divisions, right? That's the period just in terms of divisions. So 3.8 divisions, and multiply that by the seconds per division. So I'd have 3.8 times 2 milliseconds. So that would give me 7.6 milliseconds. 7.6 milliseconds is the period of this note that I was humming. Okay, 7.6 milliseconds. And if I want to know what the frequency of that is, well, I just have to take the reciprocal. 1 divided by 7.6 milliseconds. And that will give me the frequency, at least to some reasonable value. Okay, so if I'm just going to do this over here. 1 divided by 6 milliseconds, and I get a frequency of 130, let's just say 130 hertz. 130 hertz, which is quite low. And that kind of makes sense because I have a low voice, especially when I hum or sing. Okay, so that's basically the idea. If I try to hum a higher note, what do you suppose will happen to the waveform? If I hum a higher note, will the waves be longer? Will the period of the wave be longer or shorter? If I sing a higher pitched note. Okay, make a guess. All right, made your guess? So let's try it. So I'm going to hum a higher note. All right. I'm a bit warbly today, but anyway, in this case, it kind of looks shorter, doesn't it? And I can, oops, and I can adjust the horizontal offset again, like so. So if I start my wave on this square right here, I have 1, 2.2 divisions is the period. And then if I multiply that by the seconds per division, then 2.2 times 2 milliseconds is 4.4 milliseconds for one period. And then I can go back and calculate that frequency, and it's 220, say about 230 hertz, which is still quite low. But like I said, I have a relatively low humming voice. So that's basically the idea. All you're going to be doing in this case is basically counting boxes. You first have to identify where the waveform starts, and as we do the lab, I'll move it around so that to hopefully guide your eye. And then you just need to count boxes and multiply the number of boxes by the seconds per division to get the period. It's really important that you get the period, otherwise it's going to be really difficult for you to do anything else. Okay, folks, I hope that little intro there to an oscilloscope kind of made sense. I know that some of you are probably still a little confused about the whole idea of what the period is and how that's going to be useful. But I'd like you to just pay attention now, because what I'm going to do is I'm going to play a couple of notes on an instrument that I basically cobbled together here in my room. So in this case, I have this one. This is just a plastic PVC tube, which I'm not entirely sure how long it is, but I've made some markings on it, which will tell me how long it is from here. So I don't know if you can see, but there's a 30 here that refers to 30 centimeters. So from this, here, I'll do it this way. From this marking to the end, that's 30 centimeters. All right. And now what I'm going to do is I'm going to take this and put it into a jug of water, right? I have this jug of water. Check this out. And so then if I dip this one into the water and I put it at the 30 centimeter mark, now I have an air column which is 30 centimeters long. And so when I blow across the top like this, it's going to make a noise according to an air column that's 30 centimeters long. The water in this case, the water acts as that hard barrier, because when the sound waves reach the water, they're going to bounce back up. So this is an example of a closed air column. One end is open, that's the end I'm blowing in, and the other air is closed, that's where the water's at. So what we're going to do now is we're going to flip over to the virtual oscilloscope and see what it tells us about the sounds that are coming out here. Okay, so I'm going to be playing a bunch of different sounds. I've made like a lot of different markings on this thing. So I'm going to basically play a sound, freeze it, move the waveform around so that hopefully you can measure it on your screen or look at it on your screen. And then that way you'll be able to tell the period for each of these notes that I play. At least, well, we'll see what happens. Okay, everyone, so I'm going to start off at 20 centimeters because the way I've cut this tube, that's about the shortest I can get. So this first one is 20 centimeters. Here we go. Ooh. Okay, so there's the waveform for 20 centimeters. And what I'm going to do is I'm just going to put this highest point. This is kind of a complicated wave, but I'm going to put the highest point along the y-axis. And so hopefully you can measure backwards to the highest point of the next wave. And let's see. Let's do this one together, okay? Because this one's a little tricky. So if I start here at 0 and I go 1, 2, 2.5. 2.5 divisions at 1 millisecond per division means my period is 2.5 milliseconds. Okay. For the next one, I'm going to go to 22 centimeters. So my length is 22 centimeters. Here we go, 22 centimeters. All right, something like that. Now, there's lots of ways to measure the waveforms. If you have a really jagged pattern like this one, if you see a feature that repeats itself, then you can use that. So in this case, I'm going to choose this middle kind of crest here. And I'm going to move that. Oh, I can't move that middle crest onto the y-axis. That's too bad. Okay, well, I'll move it there. So from this middle of this crest, I should say, we're going to count backwards to the middle of the same feature on the previous crest. So we're going to go 1, 2, 2.8. 2.8 milliseconds. That was for 22 centimeters. Okay, now we're going to go to 24 centimeters. 24 centimeters. Here we go. All right. Let's move it around. Something like that. Okay. I would start from the middle of this crest, and then, or the middle of this one, doesn't really matter, and then go to the middle of the next one. How many milliseconds is that? What's your period there? Now we're going to go to 26 centimeters. Here's 26 centimeters. All right. That was 26 centimeters. And if I adjust this a bit, okay, something like that. So again, if you measure from the middle of this waveform to the middle of the previous one, sorry, middle of this crest, I keep saying waveform, the middle of this crest to the middle of the one before, and get your period. Next, we're going to go to 28 centimeters. 28 centimeters, here we go. All right, nice one. So if I move that one there, so if I look at the middle of this crest and measure backwards to the middle of this crest, how many divisions is that? All right, we got two more. Here's 30 centimeters. 30 centimeters. Right. Quite low now, or at least so it seems. So if you measure from the middle of this crest to the middle of this crest, how many milliseconds is that? All right, this is going to be the last one. This is 32 centimeters. Can't really go much past this. So 32 centimeters. Here we go. This one's actually quite hard to make a noise, so we'll see if it works. 32 centimeters. All right, not too bad. Okay, something like that. So if you go from the middle of this crest to the middle of this crest, how many milliseconds is that? All right, folks, that's the data.